Hello, I'm Ralph Gable of the Electronics for the Inquisitive Experimenter YouTube channel. This is the fifth in the series on vector network analyzers, or VNAs. In the previous videos, I talked about what is a VNA and why do I even care to use one. What kind of measurements can I do with my VNA? What are the terms that I need to understand if I'm going to effectively use my VNA? And single port calibration and measurement. This video was going to cover the entire topic of two-port measurements using your VNA. It was going to include all of the foundational stuff that you need to know, plus demonstrations on making these measurements, but it ended up being way too long. So I broke it up into two pieces. This particular video is going to be all the foundational stuff, the explanations, what two-port measurements is about, the things that you have to be concerned with, and all of that kind of thing, so that when you go into the demonstration, it makes sense what you see. The demonstrations will include doing a two-port measurement on something like this Wacom bandpass filter. It's a VHF bandpass filter. So we'll actually do the measurement on this filter using both the Mini VNA Tiny and the Tektronix higher end VNA. The other demonstration will be with an active device, an amplifier. This little amplifier here has a receive preamp in it, which is rated at 20 dB of gain. And we will actually be measuring the gain of this preamplifier using, again, the Mini VNA Tiny and the Tektronix VNA. So, if you find this video helpful, please click on the like and subscribe to the channel so that you will get notifications when new videos come out. So let's go into two-port calibration and measurement, the foundations. So let's talk about some background with regard to two-port VNA calibration and measurement. With some VNAs, two-port calibration and measurement, the two-port measurements are referred to as S21, which means the signal is starting at port 1 and going to port 2. And the higher end VNAs will let you go the other direction and refer to it as S12, so the signal's originating on its port 2 and going to its port 1. You also have other VNAs will refer to it as response or through or transmission. And so the whole idea with this two-port measurement is that a signal is sent out of one port of the VNA to the unit under test, or UUT, and the output of this unit under test comes into the second port of the VNA, and the VNA is over here listening to this, to the signal that it is getting here, and it is measuring the amplitude and phase of that signal. Now, that is the information that it takes and formats that in whatever thing that you happen to be interested in, going through the mathematics of turning it into whatever it is that you need to be looking at. You might be interested in, for instance, if this were a filter or some kind of passive device, you might be interested in its insertion loss, which is a loss. Or you might be interested in the frequency response of this filter, which again is kind of a form of loss, because you're looking at how it's bumping along through the frequency range and where the dips are, but it's still, you're getting out of the device less than you're putting in. So these passive devices like this are that way. Or you could be doing an active device like an amplifier. And this, in the case of an amplifier, you would have a lower on the input than the output because the amplifier would have gain. You'd still be interested in the frequency response. How much gain does it have over its rated frequency range of the amplifier? Now, the reality of measuring these things is that any change in how you connect up to the unit under test is going to make a difference in the measurement. So let me give you a quick example here. Suppose we have a unit under test here, and it is some unit, doesn't passive or active, it doesn't matter at this point, and we are choosing to connect the unit under test with a 5-foot piece of coax, and the other side here is a 5-foot piece of coax. So between the VNA port 1 and the unit under test, we have 5 foot of this RG58AU coax. Specifically for this is this Belden C1178. And then between the unit under test and the port 2 where we're listening is another 5-foot piece of coax. Now if you were to go out to the data sheet for this specific coaxial cable, you will discover that at 435 megahertz, and in fact this unit wants to be at 435 megahertz. Let's say it's a filter or other such thing here. And so we're interested in its response at 435 megahertz. So you go out to the data sheet for this RG58AU and you determine that according to the data sheet, these pieces of coax have an attenuation of 12.7 dB per 100 foot. Well, that doesn't seem like it's I mean, that's per 100 foot, you know. Well, we got 5 foot here and we have 5 foot here. And so if you have 0 dB going in here, by the time you get to the other end of this cable, it's going to be down by 0.635 dB, and then it goes through the unit under test here, comes out here at some level, and it suffers another 0.635 dB of attenuation through this cable. So in the end, the magnitude that you're measuring over here is going to be 1.27 dB lower than it would be if because of these cables. And so if you were to have these cables in place when you did the calibration, this aspect of these cables would be calibrated out and you'd only see the unit under test. But what about phase? There's another aspect of this because we're at 435 megahertz. You got 5 foot of cable here, 5 foot of cable here, and the phase of the signal changes as you move through this cable. And it turns out that because the velocity factor of this particular cable is 0.66, these 5 foot pieces of cable are approximately 3.35 wavelengths long. So you got 3.35 wavelengths on this side, you got 3.35 wavelengths on that side. Now, the full wavelength isn't going to be an issue. I mean, if this was exactly 3 wavelengths long, phase-wise it would be, well, invisible. But it isn't. It's 3.35. So you're shifting here, in addition to the 3 wavelengths, 126 degrees of phase shift. That is a visible phase shift through that cable. And then it comes out here and it shifts another 126 degrees. So in the end, you've got 252 degrees worth of phase shift because of these cables that does not represent what the unit under test is doing. On the other hand, if you calibrated your VNA with these cables in place, then the VNA will calibrate that out, and all you'll see is the phase shift of the unit under test. So, with all this in mind, let's talk about preparing for calibration and measurement of a two-port device. Well, before we get into the nuts and bolts of preparing for calibration and measurement, we need to make sure that we are on the same page regarding attenuators. I know when I was first into technical training school and they started talking about attenuators back in the Air Force, I went, huh? What's that? So let's just take a few moments to talk about what an attenuator is. Basically, an attenuator is a device that reduces the amplitude of a signal by some predetermined amount. You put in 1 voltage and you get a lower voltage out. So V out is less than V in. You can kind of think of it as a voltage divider. And depending upon the values of R1 and R2 will determine how much this input voltage is divided down to the output voltage. But in the RF world, it's a lot more than that because it needs to be impedance matched to the system that it's inserted in. That means that if we have some kind of signal generator over here and it has a characteristic impedance of 50 ohms, it wants to see this be 50 ohms. And if we have some system out here and its input, it has a characteristic impedance of 50 ohms, then it wants to see 50 ohms looking in through this direction. Well, you can kind of guess by looking at this that you're not going to get that with this particular way of doing it. So what we do instead of that, we have a T configuration. This is one way they do it. And so there is our other resistor, R3. So now, looking in this direction, this is 50 ohms. Looking in this direction, this is 50 ohms. And it doesn't matter which way you go, this voltage divider will divide down by the same amount. But you know, there's more to it than even this, because this is an AC signal source and there are stray capacitances and you have inductance associated with the leads of the resistors and whatever else is part of this thing. And so it's not going to be perfectly flat across the frequency range. So you have to be really careful when you put together an attenuator to minimize your capacitances and your inductances and make sure that things are matched in such a way that over the frequency range that you plan on using this, it has a consistent attenuation level, because all of that capacitive stuff makes a difference. Now, no attenuator is perfect no matter how much you pay for it. So how much is good enough? Well, I mean, you could spend hundreds and thousands of dollars on an attenuator. But do you really need that kind of accuracy? Do you really need to spend that kind of money on it? Well, that entirely depends on what you're trying to do. And for most of us, we don't need that kind of precision and accuracy. We just need something that works. So, now on to our treatment. of how to do the preparing for two-port calibration and measurement. One of the first things that we have to consider are the levels associated with the measurement that we're going to be making. It's not too much of an issue with passive devices, but with active devices it definitely can be. First, we have to consider the unit under test input level capabilities. The actual amplitude of the source signal from your VNA is really not a very big signal, but it could still be more than what your unit under test is capable of handling. My mini VNA Tiny has a stated stimulus level of -6 dB, and there's absolutely no adjustment. It is what it is. And if your unit under test cannot handle -6 dB, then you need to put an attenuator between the VNA and the unit under test in order to accommodate your unit under test limitations. On the other hand, my other VNA, my Tech VNA, it has a default power level of 0 dB, but I can adjust that power down to accommodate my unit under test. Now even that has limited capabilities. So like my many times ancient Hewlett-Packard circa 1986 VNA will only adjust down to -10 dB. Well, if my unit under test can't handle -10 dB, I'm still going to have to stick an attenuator in between the VNA and the unit under test. Now, one good example of having to pay attention to the input signal levels might be a receive antenna preamplifier, which is expecting signals that are coming in on the order of -20 dB or even lower than that. I mean, S9 on your radio, on your S meter, is -73 dB. And of course your S meter might go up to plus S9 plus 60, so we'll do the math later on that. So that means that this signal level here needs to be -20 dB or lower. You either have to attenuate the VNA's stimulus signal to accommodate that, or you're going to have to adjust the stimulus power level to accommodate it, or maybe a combination of both. But that's not all. There's also the VNA input capabilities. I mean, if it's a passive device, you don't have to worry about it again, because by and large, with a passive device, the power going into the unit under test is going to be higher than the power coming out. But with an active device that has gain on it, well, that's a different story. Suppose this unit under test was very happy to accommodate a 0 dB stimulus signal, and you put in your 0 dB on the input of the unit under test, and it has 20 dB of gain. Well, guess what's coming out over here? Plus 20 dB. But can your VNA handle the signal that high? Well, even my high-end VNA only wants a maximum of plus 10 dB. The mini VNA Tiny also will accommodate plus 10 dB, but when you look at the software on the screen, the highest you'll ever get it to display on the screen is 0 dB. So obviously then, in that case, you have to keep this level below the VNA's capabilities by changing the input level delivered to the unit under test. Alternately, you could put an attenuator between the output of the unit under test and the input of the VNA. So in this case, if this unit under test has 20 dB of gain and the input wants to be 0 dB, you got 20 dB here, you put an attenuator in here to bring it down below the VNA's maximum input level. So now we need to consider the cables and the attenuators and the adapters and everything that you're using. So we know that the first rule of two-port VNA calibration is very similar to the first rule of one-port VNA calibration. Always calibrate your VNA with all of the cables and adapters in place that you're going to use in the measurement. And if your VNA allows you to do so, even include any attenuators that need to be in the system in the calibration step. And this raises the question, calibrating with the attenuators in place. Well, you might be able to calibrate your VNA with all of the attenuators in place, but you might not. With the higher end VNAs, there's a good chance that you'll be able to set up all your stuff, leaving the unit under test out of the whole thing, replace the unit under test with a one-to-one adapter between the ends of the cable, and do the calibration including the cables and all of the adapters and the attenuators in place. And this is a great way to do it, because then everything, the effects of everything get calibrated out. And then the very next thing, when you hook up your VNA to your unit under test, all you see on the screen is the response of the unit under test. Now, not every VNA is going to let you do that. Their less expensive cousins may not accommodate that. I know I tried to do that with my mini VNA Tiny, and well, the measurement was kind of like garbage. It wasn't even worth trying. Now, I can do that if I don't have that much attenuation in line, but this, I was trying to do it with 35 dB of attenuation, and it just did not, it let me do it. It just didn't end up with anything usable in the end. So the resulting measurement, if you calibrate it with let's say you're doing an amplifier, and you can calibrate because you're not using that much attenuation, and so you can calibrate with the attenuator in place, like with the mini VNA Tiny, and the output amplitude of this amplifier is within the limits of the mini VNA Tiny and all that kind of good stuff. But the software is not going to display anything above 0 dB. So if the response ends up above 0 dB, you can't see it on the screen. Now, you can export the data to a CSV or Excel file and then open that file up in a spreadsheet program and see the data that way. But I will tell you how to accommodate this limitation of the mini VNA Tiny with the amount of attenuation we'll need for our demonstration. As we go through the demonstration, I'll show you how to do that. But for you and your particular VNA, the only way you're going to know what your particular VNA will do well is to experiment, play with it, see how it does things and what it will let you to do. And as before, I emphasize again, every cable and every adapter does make a difference in the measurement. As to whether that difference is enough to be concerned with, that's entirely up to you and what you're trying to do and the precision and the accuracy of the measurement that you're interested in. So, you gather all the cables and attenuators and adapters and all of that stuff that you need for both calibration and measurement in preparation for doing your calibration and measurement. Next, we have to consider the frequency limits that you're calibrating and measuring to. Now, some VNAs will let you set the frequency limits of the calibration. In this case, it's important to set the frequency limits before you calibrate, because the narrower your frequency limits are, the less interpolation there is between each of the samples it takes to set up that calibration. You might want to add a little bit of elbow room in there this is your choice. For instance, if we're looking at the 2 meter band, which runs from 144 to 148 megahertz, you might set your limits to 143.9 to 148.1. This is your choice, or you can just do 144 to 148. Now, if you calibrate to a wider frequency span and then measure to a narrower one, that's okay. You don't want it too much wider. You want to try to keep it as close as possible. But you definitely don't want to calibrate it to a narrow one and then measure wider. That's a kind of a big no-no. Now, some VNAs, like my Mini VNA Tiny, they do not allow me to set frequency limits before calibration. It calibrates the entire frequency width that it has capable, and as a result, you end up with a lot of interpolation between points, possible inaccuracies. Now, you can cause some VNAs to use more calibration points, which narrows the distance between any two calibration points and reduces the interpolation. That's one way to do it. In the Mini VNA Tiny, they have Mode 1 calibration, which if you carefully follow the instructions in the software manual, there is a file that you can edit, but it's still going to require you to calibrate the entire frequency range of the device. If you don't cover the entire frequency range of the device, it throws the file away that you just edited and sticks its own in there. Now, so you look at the device, you can figure out where your frequency limits are, and you get ready to do your calibration. So next, we're going to be talking about stepping through this process of calibrating, and then we'll go right into our demonstrations. And so let's now step through the calibration process for a 2-port calibration. Now, to calibrate your VNA for a particular measurement, you may need known to be good standards to do that, and the laboratory quality standards of this type can be very expensive. But for the sake of what we often do, we don't need to have that kind of expense associated with it. Now, you'll need at the very least, if you do a complete 2-port calibration, and again, this depends on your particular VNA and the kind of measurements you're trying to accomplish as to whether you'll need, what you're going to need of any of these things, but I'll talk about that in a little bit. One of the things that they're going to want is an open. And an open needs to be a complete connector. It's not just simply not connecting something to the port or the end of the cable. And so here's my open that I used for a long time. It's just a connector with the center pin missing. You can also have a female version, the female version here. This is a really cool standard here. It has a short on one end and an open on the other, and it just looks like that. The commercially available opens, very similar to what I just showed you with my homemade open. It's a complete connector with just a hole right down through the middle of it. And then you have to have a short, which is exactly, in other words, it's still a full connector. You can see the full connector, and the center pin is there, and I have it big blob of solder, soldering all that together. You can get commercial shorts that are much nicer looking, but still accomplish the same end. And then I already showed you this really cool female one that has a short on one end and an open on the other. And then you'll need a load This is just a standard load. It is not a super special, expensive VNA calibrating load. It's just a high quality termination that you can get at a lot of the RF shops. And that's what I use for my standards. They also have female styles of the same type of thing. And that's sufficient for the kind of things that we do. And then finally, see, those are all the standards you need for doing a single port. But you'll also need a means of connecting the two cables together, and this is just a female to female N-type adapter that I use for a through standard. Again, we don't need all of this real fancy schmancy, very high-end, very expensive stuff to do the kind of measurements that we're going to do. Now, to get the most benefit out of calibration, I'm going to say it again, do it as close as possible to the unit under test, include all the interconnecting cables and the adapters and if possible even the attenuators in place. Now, for the calibration, like the mini VNA Tiny and even my higher end VNAs, I can, when you do the 2-port calibration, the mini VNA Tiny and my high-end VNA will let me do this too. Part of that is these 2 ports on the VNA are left wide open. Nothing connecting, just hanging out there. This is known as isolation. They're trying to see how much of this source signal that is present at port 1 or your device under test port, whatever your VNA calls it, is going to be present on port 2, the detector port, when the cables are not connected. Now, this is also going to be affected by if your cables are laying next to each other, you know, because coaxial cable isn't perfect. They leak signal. So if you want the isolation portion of this to be as good as possible, you know, you have your cables separated far enough that whatever signal leakage happens on one isn't going to be leaking into the other one. So there's the open. And then the second step they have you do is then they have you put your through, which is just your adapter to connect the 2 ends of the cables together. Now it's measuring through this whole loop here, the signal levels here that are getting from here. It's measuring the amplitude, it's measuring the phase, and so now it knows that if there's no device under test connected and I'm just connected end to end, this is what I can expect. That way, when you put your device under test in here, it says, something is different. So the other thing that VNAs will let you do, and I know that my higher end VNAs will do this, you can have what one VNA calls an enhanced 2-port calibration. It actually does a 1-port calibration on the source port and then a 2-port calibration between these two. So that way, when I connect this up to some device under test, I can actually measure the return loss or the SWR or the impedance of my device under test, the input of my device under test, as well as the through, the gain or loss of that device, which is pretty cool. Now the mini VNA Tiny, if you calibrate it, do a 1-port calibration. Look at the last video on 1-port calibration and measurement. If you do a 1-port calibration and then turn around and do a 2-port calibration, you have that same advantage. You can jump back and forth between reflection and transmission with that one. So let me go through this entire process, the calibration and the measurement, using my mini VNA Tiny as one of the examples, and with my higher end VNA as the other example. And I want to measure two different kinds of things. I want to measure the response of a Wacom bandpass cavity, which has its resonance in the midst of the 2-meter amateur radio band, and also an active device, which is an RF receive preamplifier with an advertised gain of 20 dB across the 2-meter band. So let's see how all of that works out when we go to measure it. So there you go, the foundational information that you need in order to do 2-port VNA measurements. In the next video, we are going to be actually doing the demonstrations on how to make a measurement on this passive device. It's a Wacom bandpass cavity. And then also on this active device, which includes a receive preamp in it that we're going to be measuring its gain. If you have found this video helpful, please click on like and subscribe to the channel so that you will get notifications when new videos come out. In the meanwhile, stand by for demonstrations on these things, and thanks for watching, and toodaloots.